So again, today's goal is the same as yesterday. Yesterday we started learning about asymptotes being vertical, and then we quickly mentioned the term hole, so there could be a jump in the graph, or a gap in the graph. Now, today we're doing the same thing, but we're going to start determining that hole, the value of it, and we're going to then say, what is the difference? When do we have an asymptote versus a gap in the graph, such as a hole or discontinuity? So we're still doing the same thing. We're looking for discontinuity. Who can tell me? When do I get a discontinuity? What causes a discontinuity diagram? Algebraically, what causes it? Good. So you can say like an asymptote. Remember, the asymptote is the curve is closer and closer and closer to the vertical asymptote of mushrooms, and delta x, being that little gap, keeps on decreasing. That's one way to think about it. Absolutely. Algebraically, now that was graphically. So I asked algebraically. Julia was nice enough to give us graphically. Algebraically, what causes a discontinuity? Which part of the equation? What is that called? The bottom. What is it? Denominator. Okay, so you have to out there. Because remember, you can't have 0 in the denominator because dividing by 0 is undefined. So there's no definition of the function. Thus, there's no function value. That's where a whole comes about. It's like saying the whole function is continuous. It's got all these values, but then when you get to that one spot, there's no value of it because of that 0. That's what the whole is going to come into that. Now, the numerator we're going to see on concept 45 tells us about the roots and what the roots will become. Okay, if we set the numerator to 0, we get the roots. So it is important to mention that we are really looking at the denominator today. Again, we're always looking to see when the denominator itself is equal to 0. That causes a discontinuity. Now, what you're going to notice in this problem that we're about to start is that the numerator as well can be factored here. Okay, if you look at the numerator right away, you can see that it can be factored. There's no substitute. So for this problem, what we're going to do is we're not only going to take a look at the denominator, but then afterward, we're going to compare it to part of the numerator and see if we notice any, not irregularities, but common factors. So take a look at the denominator, please. Everybody factor your denominator right away so that you can see what would cause it to be 0. Again, you always look at the factors, people. Always, always, always look at the factors. What does this factor into?
X minus 6.
Everybody agree?
Yeah.
I agree as well. Now, once I've done that, what can I see? What will cause this to be 0? What will cause this factor to be 0? Positive 6. So x cannot equal 6. That's one of our restrictions to our domain. Good. X cannot be equal to -2. So far I've determined the values of x that cause g of x to be undefined. But now what I want to start doing is classifying them, because they're not both vertical asymptotes this time. One of them is actually a hole, and here's how we're going to be able to determine it. I'm going to show you guys experimentally, again, if we look at a data table. Remember how last time we looked at data on a table, and we saw that it was going to infinity, okay, and it was going to negative infinity, to show that the asymptote was really merging together like this. Okay, this part was going up to infinity, this part was shooting down to negative infinity. And we looked at the data last time with 5x values. Today we're going to do the same thing. What we're going to do now, though, is first we're going to take a look at the value of x equals -2. X equals -2. For x equals -2, what are we going to notice here? What do we want to choose? What kind of points?
Positive. Wait, what?
For this kind of a problem, people, what do we want to do here for -2? How do we want to figure out what's going on there? What kind of points do I want to choose? Okay, something like that, good. So let's start making a data table here. X and g of x. let's go ahead and say, all right, I'm going to choose points like negative 2.1, negative 2.01, negative 2.001. Maybe choose points like that. And then from the other side, how do I approach it? What's lower than negative 2, absolute value-wise?
Oh, 3. But no.
No. Go the other way, guys. We did
1.99.
good. 1.9, so negative 1.9, negative 1.99, negative 1.999. So what we're going to see is we're going to see what this number is approaching on both sides to look for what the actual value is. If it is infinity and negative infinity, if it's getting bigger and bigger and bigger, then we can say it's probably an asymptote. That's what a vertical asymptote is. We talked about that yesterday. That number kept increasing. That's what caused it to be an asymptote. Because one side was going off to infinity, while the other side was going off to negative infinity. So what I want you guys to do right now is please open up your calculators, go to Y1. When you're in Y1, type this function and take a look at the board, please. Make sure you have parentheses. And Derek learned that yesterday. We all learned that one. I've done it myself. Make sure you have parentheses, please. Did anyone print out the notes ahead of time?
You changed it again?
No, but there's a typo I just noticed, and it's bothering me a lot.
Are you gonna fix it?
I'm going to, yeah, but not right now. Next period. During second period.
I'll let
Yes.
How do we calculate?
I looked at this point, and I started by saying, what are some numbers around it? And I wanted to get closer and closer. So like, if I had 2.1, that's close to 2, but 2.01 is even closer. 2.001 is even closer. So I'm trying to come closer and closer to it, because I know if I plug negative 2 in, it's not going to work. This becomes 4, this becomes 8, 4 plus 8 is 12, 12 minus 12 is 0. So I can't plug in a 2 to see what the value is. So I'm going to approximate it by looking at the values near it. I'm going to take a limit, or I'm going to hone in on the target. The target right now is negative 2. I want to get to negative 2. But I can't do that, because if I plug negative 2 in, it becomes undefined. So I look at the values really close to it, because they provide a good idea of what it looks like, right?
How do you know, do you put the 6 number or 6?
No, I just, sorry. Yesterday I did 5 on one side and 5 on the other side, right? Five of these, like this. Yesterday I did 5 from the right, or in this case the left, sorry. And 5 from the right. Today I'm only doing 3. Because I don't need as many, and you'll notice that right away. All right, people, can I get somebody to raise their hand and give me some numbers? Jay.
The first one is
Can we verify, please?
negative 0.2469.
Agreed? Others?
The other one,
I need everybody to agree before I continue. I did this yesterday.
oh, I didn't close the parentheses.
Okay, close them and then tell me the new number, Jason.
So, the first one is 0.01251.
We all agree with this?
Hey, you didn't put the parentheses. So
Who did put the parentheses? Derek.
I was like the
First one was negative .2469.
You're missing one right here.
Jason, isn't that what you started with? Okay, is that correct?
Yeah, I got that.
Jason, continue.
Okay.
Thank you, Derek.
And the other one's negative 0.2497. Next one is negative 0.25.
And it stops?
No. The next one is negative point.
No. Are there any more numbers?
No.
All right, interesting.
The other one's negative 0.2532. And the other one is negative 0.2503. And the next one is negative 0.25.
Okay. So here's what we're noticing. These are the values that we're honing in on from the left. This right here, this is from the left. And how do I know that? If I were to graph this function, and I wanted to find out at -2, so here's -1, here's -2. I wanted to look at the behavior of the graph at -2. I need to pick some points to the left of it. That's these 3 points. And it's clear to me that it's honing in on what value here. Anyone else see this or no? No one said it yet. What is it honing in on? What is the value of the function getting closer and closer to?
0. -2.
No,
Okay, that's where it's tough. All right, let me give you a better example then.
it's not getting closer to 0. It's actually getting moving further away.
Not further away. Take a look. This is a number. Please ignore the negative sign for a minute. Everybody make believe it's not there, because I know this confuses people. This number is close to 1/4. 0.25 would be a quarter, wouldn't it?
Yeah.
And this one, isn't this getting closer to 0.25?
Yeah.
This is missing 0.25 by what looks like 31 thousandths. This is missing 0.25 by 3 thousandths. Or wait, let's see. Tenths, 100 thousandths? No. By 3 10,000ths. Very small number. This is pretty much negative 0.25. What's bothering me right now is because I screwed up the notes for mine. These numbers would have been better if we did it with a different value. Because this is the value that it's honing in on, the negative 0.25. It just happens to get there. Which I said a minute ago, remember? It can't really get there. Okay, it's getting closer and closer. The issue is, Jason, when you read this number, it was 2500, or just 25? When you plugged in negative 1.999, did it round that, or did it do anything like that?
No.
It kept it all like that. Very interesting. Very interesting. Because this number is not exactly that. If it was nines repeating forever, then theoretically it would get there. But I feel like there should be more decimals on this. Like the calculator's cutting us off a few of them. But here, in these 2 spots, it's really approaching negative 0.25. So here's what I see when I graph this. I see at negative 2.1, I'm close to negative 0.25. So I'm like here. Then I see at negative 2.01, I'm getting even closer here. Then around negative 2, you're getting even closer. I'm going at an angle, sorry. Now, that's from the left side. I'm going to try and blow this up because I can see you guys can't see that there. Okay, here's what I'm trying to talk about now. On the left side of 2, at negative 2.1, here was the point right here. At negative 2.1. Then at negative 2.01, it got closer to negative 0.25. Then it got even closer right around negative 2. Then on the other side of negative 2, so at negative 1.9, it was, let's say, right up here. Then at negative 1.99, it was here. At negative 1.999, it was here. So it's pretty much getting closer here. But right here, we're going to have an open circle there. Because again, at negative 2, the function has no definition. Because the denominator becomes 0. So at negative 2, we got to go back and remember that it has no definition. Okay, again, it has no definition here. So we have some sort of a hole going on there. Now, for the sake of time, go ahead to your calculator and look at the graph now. Go into your calculator and look at the actual graph.
Why is it like this?
Okay, what you're going to notice is several things. First, Okay, let's take a look now. So again, guys, if you look at the notes right now, they're a little bit off. I used positive 2 as my whole by accident instead of negative 2. Okay? That was why I was trying to figure out why my numbers were off when I was doing up here. All right, so first of all, what do you see is going on around 6? It's got that shape, right? What did we call it yesterday, guys?
No, not asymptote.
Yeah?
Oh, asymptote.
Asymptote, very good. So at 6, we're going to see clearly that there's actually a vertical asymptote going straight up and down. Okay, that's what we had yesterday. Because take a look at one of your denominator's roots. One of the denominator's roots turned out to be 6, and the other was negative 2 that we looked at. But here's the problem, people. Take a look at negative 2. I don't see a hole there. And on your calculator, if you zoom in, you're not going to see one either. The calculator will never show you the holes. But we know that it does exist. So when we graph stuff like this, that's how we graph it. And you actually put an actual circle there and get rid of the line that's in behind it. So you actually want an open circle. So graphically on here, this is how I would do it. I would go ahead, and since I knew the point of the location of it, I would type in negative 2 comma negative 0.25, and that's where the hole would be. Okay, that's where the hole would be at A. So just to show you, because I know you guys are going to have questions on this, because you're going to do a portfolio on this one eventually too. You are, yes, I know.
Are you sure?
I'm sure.
You're extremely positive.
Okay, that's how you demonstrate a hole. Okay, so the graph kind of like stops there and has to jump over the hole to continue. That's why it's a discontinuity. And again, at x equals 6, there's also a vertical asymptote. Let's see. What else? What else? Okay, let's go to the last point that we want to make here. Let's go to the last point to make. For this problem, we factored the denominator. Somebody tell me, what does the numerator factor into?
2 times x, 2x.
Very good, right? 2 parentheses x plus 2. How do we say that? We should really say 2 times the quantity x plus 2, right? Parentheses means the quantity. All right, now, focus please. Look at your denominator. Look at the numerator. What's common to both?
X plus 2.
And wasn't that where my hole was actually at negative 2?
Yeah.
This came to negative 2 from this right here. So one of our ways to know that it's a hole and not a vertical asymptote is if you have a factor in both, the top and the bottom. That's one way. So please write that down for the first way. So if you have a factor that repeats itself in the numerator and the denominator, it is a hole. That's another way, a simple rule to determine that. If you have the same factor in the numerator and the denominator, then there is a hole when that factor equals 0, which is what we did. We said it equals 0.
So wouldn't it make sense to factor the top to put it
Absolutely, to tell you, so not to use that table, right?
Yeah.
I don't want to do this every time. So you simply do that. But now comes the question this, guys. If I didn't use the table, then how am I going to know what the value of the hole is, really? See the negative 0.25 I circled over here? Okay, again, right here and right here. That was the value or the height of the function, or the value of the function there. That's where we put the point. Remember that open circle we had a second ago? There's that open circle. And what's its coordinate? There's the negative 0.25 up here. Okay, that's the negative 0.25 that we got from this part. Now, how do I know that value? Here's a little trick for you. Here's a little trick for you. Cancel out the x plus 2's. Since they're in both. Write what's left. Okay, write what's left. Now plug negative 2 into that. Now plug negative 2, because that's the point we want to look at. We're trying to find out where the hole is. That's the x value. Now plug this into the new function. You get 2 over, again, this becomes 2 over negative 2 minus 6, which is 2 over negative 8. What's that as a decimal? Negative 0.25. which is the same number you got over here. So this is, guys, this on the left is where it all came from. This is how people test stuff in the beginning. So I'm showing you where it comes from, and now I want you to use the shorter method. So again, to test for a hole, you find the same factor in both, you cancel it, find the reduced fraction. This is where concept 38 comes in. We are simplifying a complex, or we're simplifying a fraction right now. Concept 38. Once we simplify that, we then take whatever the root was in the denominator, this one that caused the problem to be undefined, we take that and evaluate it in the reduced function by plugging it in here. We then simplify what's left over. We see that we get the same decimal that we had all the way over here. Okay? Now, the way I just showed you with canceling the factors is one way to determine if it's a whole. There's another way also. That's even easier too. And it's up to you to choose which way you want to do. Because you're going to have to cancel the factors to evaluate the -2 in here. So either way, you're going to have to do this. But there's another way to test for a whole. And it's very simple. Once you find what makes this a discontinuity, take it and plug it back into the original. So plug the 6 back into the original first. What does the numerator become if I plug a 6 in there? 16. And clearly the denominator must become 0, because that's what makes the denominator 0. When I plug a -2 up top, what do I get?
8.
Trayvon?
You get 0.
You get 0. Good, Trayvon. 2 times -2 is really -4 here. -4 and +4 is 0. So we know that 16 over 0 is undefined, or the limit of it goes to infinity, we've talked about, but it's undefined. But 0 over 0, that poses the question, well, I can't divide 0 into anything, surely, because it just never goes into it. 0 into 16 will go into it forever. 0 goes into 16 an infinite amount of times. But how many times does 0 go into 0? Do we know?
Once.
Undefined.
Once, we're not sure. 0, undefined. Okay. The reason you guys are all giving different answers is because it's called actually something which means indeterminate, which means we actually don't know. Because depending on which 0 is bigger or smaller, you don't know what's happening. I know it makes no sense, but both of them are empty quantities, aren't they? So they can't actually go into each other. So if one of them is bigger than the other, you could determine it. But that doesn't make any sense, right? Because no 0 could be bigger than another 0. So when you get 0 over 0, that's what also caused the whole. Again, we said that if we have a factor and they cancel, we have a whole. But now I'm also telling you that if we get 0 over 0, if we get 0 over 0 and we plug it back in, that's also an indication of a whole.
So I'll be able to get the
Okay, but very good. If you use the method and you get 0 over 0 and you haven't factored yet, to get the -2.5, you're going to have to factor. You're going to have to cancel your factors like that. Then you're going to have to plug that number into what remains. So either way, you're going to have to factor. Okay? I'm just telling you guys where the word indeterminate comes from. It comes from 0 over 0. So ignore the graph because this graph is not correct. Again, that was the typo. Let's just look at the conclusion. Conclusion. If the value of the function at a discontinuity is at a discontinuity is indeterminate, if it's indeterminate, which is 0 over 0, then there's a hole at that location. And again, the second sentence says the next. You can think of this as having, same thing we said a minute ago, the same factor in the numerator and denominator. Okay, that's how I want you to think about it, one or the other. Remember though, you must factor to find the value of the function. You must factor to find the value of the function. One more to go, guys, and you'll have a little bit of downtime. I know it's not a very easy thing to comprehend.
I kept saying that every time someone messed up. I told you, no big bench. Every time we messed up, I was like, no, what's the bench?
That was like that for habitat.
Any questions so far? We're going to do one more problem. One more. I know, guys. You don't listen. You never have to make a table. I know I made one yesterday, and I made one now. For the third example, though, I'm not going to use a table. I'm trying to show you guys specifically here where stuff comes from. Not just the rule, not just the answer. It really is important to think about. Okay? If we don't know where stuff comes from, then how do we know how to build stuff ourselves, right? We're just told stuff over and over again, and we're not going to develop any original thought. So I'm trying to show you that people do have original thought, and that's the kind of stuff I want you to start really pondering.
Oh, so where do we actually look for the value?
Yes, even though it has no value because it's an open circle, right?
Yeah.
It really has no value, but we're trying to find where is it, the location. Very good. Very good. I would say even the location of the point that represents the whole. Because it is a point. It is. It's an empty point, though. Let's try this one now, please. Now, people, here comes back factoring. Remember what you need to start by finding. Whenever you factor before anything, what do you always look for?
Restrictions.
Is it? GCF. GCF first. You can't get the restrictions till you factor it. You can't factor till you take out the GCF. So you always start with the GCF, guys. Again, take the GCF out of the bottom, then factor what remains, then you can find the restrictions. So it's always GCF to start these problems. Unless you can see, I mean, clearly 0 screws up the denominator. But that's just by inspection, I can see that. Because the 0 would make everything 0, the whole problem. 0 would be 0 over 0, actually, wouldn't it? So, everybody see that right away? If you plug in a 0, everything goes to 0. So 0 is going to be what? A whole. 0 is going to be a whole. Because it's 0 over 0, actually, right? See that again?
So the origin.
It might not be located at the origin, but the x-coordinate will be 0. We then have to take that and plug it into the factored form to see what the height of it would be, or the location of the point. To find the y. So we got a factor. Let's do it. Up top. What is it?
3x plus x plus.
Very good, Vanessa.
No, it's Julia.
Julia. Really? Are you mad at me for mixing you two up?
Hey,
Have you heard each other talk?
At least you don't. At least you're not mixing up.
You have similar voices.
Trayvon, it's okay.
It's not okay. I don't want to be called Derek or John or Andrew. I'm Trayvon.
So, in the, up here please, in the denominator, notice there's an x in everything. That's your GCF. Now already, take a look, people. The x's, aren't they common factors? That's the same thing as getting x equals 0 and x equals 0 as your factors. Because what would cause this denominator to be 0? Well, x equals 0. So that's my first restriction from that one. But I have the same factor up top. Thus, at x equals 0, I already know I have a whole. Again, because it's up top and below, and because we determined in the very beginning of the problem that it was 0 over 0, or indeterminate. Okay, again, that's a whole because of the fact that this x occurs here, and it occurs up here. Same factor in both top and bottom means you have a whole. J, x plus 5. So there's my factor denominator. So, Raul, what would cause these to become 0? What value of x can I not have here? Very good. And the other one? Very good. Well done. Now, do either of these two factors appear up top?
Yes. No. No.
No. Be careful, guys. That's a +2. That's a -2. They are two completely different things. Again, look at your factors to see if your factors repeat. If your factors repeat, you have a hole. They don't. Okay, please, vertical asymptote. VA is vertical asymptote, vertical asymptote, vertical asymptote. What do you think HA will be on Monday?
Horizontal.
Very good.
It was true.
Okay. Now, let's keep going, people. Let's not stop. We're not done. Now what I need to do is this. For a problem like this, I should really start doing things like list the domain. So to list the domain here, the smallest thing I could start at, I can see that I have 3 discontinuities to say first, right? I've got a discontinuity at 0, -5, and 2. So on my number line, this is what I'm seeing. All the way from -infinity, it's included until I get to -5. Then when I get to 0, there's another gap. Then when I get to +2, there's another gap. So that's what it looks like on a number line, even though we know that the only real hole is at 0 here. This is the only real hole. What are these really? Vertical asymptotes. Okay, but the domain, you always represent the domain on a number line with open circles to show discontinuities in the domain. But really, those are vertical asymptotes in my graph. So my domain goes from -infinity all the way up that there to -5. Then there's a gap, so I put and. I go from, sorry, or not and, -5 to 0, or 0 to 2, or 2 to infinity. So how many parts of this do I have? 4. How come? How many discontinuities are there?
2, 3.
There's 3. Look, 1, 2, 3. If you cut something with 3 cuts, don't you get 4 pieces from it? Think about a loaf of bread. Cut it 4 times anywhere in the bread. 3 times. Cut a loaf of bread, no matter where, 3 times anywhere. You always get 4 pieces. So that's what you're doing right now, guys. You're splitting this domain into 4 pieces because of the 3 gaps in the river, or the 3 gaps in the bridge. Now, that's my domain. So let's start by just labeling that, sorry, domain. Next, what I also want to do is, I want to be able to figure out what this is going to look like graphically, just by looking at my locations here. So, before I do that though, I want to say to myself, how do I actually write the vertical line? How do I write the function that represents a vertical line? And again, this should have been non-equals there. What is it? Good, it's always x equals some number. So I put x does not equal -5 and x does not equal 2, right? But if you're actually writing what the graph looks like, which on the next page we're going to see right here, this graph right here, or this vertical line, is x equals -5. That's this vertical line here. So when you're labeling your graph, that's the kind of stuff you want to be writing. Here, this is the line, x equals 2. But the question becomes, where is that open circle? It's not at the origin. It's like a y-intercept, isn't it?
Yeah.
Where is it though? Let's go back, look at our problem. Remember what we said. If we cancel the factors that screwed up the problem, that caused the hole, we can then evaluate it. Come on, please listen. Please listen, don't fall behind over there. So I notice I notice x is my, come on, lift your head, please, Jason, let's go. X is your common factor. Cancel it. Write what's left over. You're left with 3 and x plus 2 up top. Down below, you're left with x plus 5, x minus 2. That's what's left over when I cancel the whole, or the x, that appears in both the top and the bottom. Now I need to take the value from the whole and plug it in to the simplified function. So plug a 0 in here and plug a 0 in here. A minute ago, didn't I say it's like finding the y-intercept? Didn't it look like that on the graph? Well, when you set x to 0, isn't that what finding the y-intercept is? How do you find the y-intercept for any function? You set x to 0. Well, we're putting a 0 in for x. That's why on the graph it looked like a y-intercept. Because I'm putting a 0 in now. What do I got?
6 over negative 10.
Very good. So 6 over negative 10, which as a decimal is negative 0.6, or negative 6/10. So when I go back to my graph now, I can clearly see, well, here's negative 1. Okay, there's negative 1, and there's negative 0.6, about halfway down. And it looks like a y-intercept because it happens to be, even though it's an open circle, so the point is not really there. Okay?
What was that?
Negative 0.6. So the location is going to be 0, comma, negative 0.6. This is the location of the hole, and the vertical asymptotes are x equals negative 5 and x equals positive 2. Okay, so here's what I want you guys to remember, because this is what's going to your quiz is going to be on. I want you to write this down, please. First, find the discontinuities by factor. Okay, again, first, find the discontinuities by factor. If you remember, though, too, you want to put in parentheses GCF first before you factor. So find the discontinuities by factoring. In parentheses, put GCF first. That's the first thing you want to do. Second, test for holes by looking for repeated factors in the numerator and denominator. Test for a hole, so you're checking for a hole, by looking for a repeated factor in the numerator, abbreviate that please, NUM, and denominator, DEN. Abbreviate your notes again. In the numerator and denominator. So you're looking for a repeated factor in the numerator and the denominator. That's the second step. Again, I don't want you to memorize steps, please, but I'm just trying to give you guidelines when you're practicing. If you practice, the 6 problems tonight that you have to practice, and then you take your quiz, I'm pretty confident that you're going to do well. And you're not going to have to memorize the steps because it will be second nature. Now, once you test it for a hole, the third step, find the location of any of the holes that may exist. And that's what we did with the 0, negative 0.6. So, find the location of any of the holes that may exist. Find the location of any of the holes that may exist. Okay? Now, please, at the end of any of these kinds of problems, list the things that were asked for. This is your first discontinuity. Second, third, you have the domain and range listed. Sorry, if you want to add that, please, you could add that. List the domain and range. You could put that before step 2, I guess, because once you find the discontinuities, even before you test for a hole, you can actually find the domain and range. Either put it between step 1 and 2, or between step 2 and 3, or just put it in parentheses. Absolutely have to find the domain. Absolutely. Okay, please. Because when you start doing this in calculus, you've got to list your domain restrictions. If you don't, it's going to cause errors along the way. Somebody else has a question?
No, I got it right.
Sure?
Yeah.
Let's see. That's pretty much it. Okay? 2 days, I know, 2 days for a concept. It's tough. This concept is not an easy one. Here's what I want you to do for homework tonight. Well, this weekend. There are 6 problems. I would like you to do exactly what we just did for the third problem. Understand? 6. You have 3 days. Thursday, Friday, Saturday, if you take off Sunday, I'm assuming. So that means do 2 problems tonight, 2 tomorrow, 2 Saturday. Please start planning mentally. Now, this is the reading I was telling you about. You don't need to do the whole thing. Just pages 1 and 2. It's 6 pages. I want you to read the front and the second page. It starts just by talking about domain, and it goes into domain of a rational function. Later on, it talks about radical functions. We're going to use that with the concept 50s or so. It also talks about range. We're going to use that for another part as well. Again, only pages 1 and 2. Is that clear? If you look on that line, you'll see that's the homework already for tonight. It says read pages 1 and 2 of the handout, complete concept 43 homework. 2 problems per night, do please. No notes needed. If you would like to write notes in the column, annotate, I always suggest that. I assume you're going to do that. So if you don't understand something, get a highlighter out, highlight it. Get a red pen out or something, circle it. Anything you don't understand, anything you want to comment on, ask a question about, you need to annotate your notes always. Even when you get a textbook in college, your textbook should not be empty at the end of the year. You should have writing all over it. Okay, it's your way of summarizing your notes. So when you go back to the reading later, you could say, I don't need to read the whole thing. I can read what I see is highlighted or what's underlined. If you like to take notes on separate paper, feel free to do that. For me, it's more work that way. So I just annotate my notes always. But everyone's different. So do what you need to do to, keep that in mind. Okay, I'll give you the homework first, so you can start it. Unless you want to all just read it right now, get it done with.
Yeah.
We could just do like 5 minutes of silent reading. Get the whole thing done with. You don't got to read then.
Yeah, go.
Here's what I'm going to do. I'm going to hand out the reading first. If you don't want to silent read, that's fine. But then work on your homework to start. Okay? If you want to silent read, that's a good idea to do it now. Just to guarantee that you're going to do it. If your brain's a little fried, that's fine, then do the homework for now. But either way, sit quietly. If you listen to music when you read, I encourage you, listen to one of 2 things. Well, one is just simply classical music is always good. The second thing is just acoustics. So something that is not acoustic, instrumental, sorry, instrumental. Don't listen to something that has words. I know that sounds weird, but just trust me on this. Try it. Try it sometime. If you ever listen to music when you read, listen to something that has no words in it. Okay? It will help you a little. Even if it's, even if it's like heavy metal guitar or something, that's fine. As long as there's no words in it. Yeah, no, what are you going to say? You should probably stop recording, right, guys? We're done?